What is up, everybody? Welcome back to my channel. This is Tony, aka One Lead Code One Day. If you're new here, this channel does one lead code per day, following the pattern of topics or series. That is, I'm going to be solving with you together on a lead code problem I have never attempted before. You heard that right, there's no prescripted answer. We're on the same page here, but don't you worry, I got you covered, and I promise that I will submit at least one average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I'm no better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. If I can do it, you can do it. It's all about learning on the go. You can think of this video as a first-person gameplay of cracking leak codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's problem. Today we continue on the series 1, everything about dynamic programming, and the problem is 139 word break. Let's get into it. Well, 139 word break, medium. Given a string S and a dictionary of strings word dict, return true if S can be segmented into a space-separated sequence of one or more dictionary words. What does that mean? Let's take a look at some examples. Note that the same word in the dictionary may be reused multiple times in the segmentation. Okay, example 1. Input S leet code, word dict leet code. Output is true. Explanation, return true because leet code can be segmented as leet code. Okay, so um, if you if you can segment, the string into dictionary the words that you can find in the dictionary, you return true. Okay, apple, um, apple, pen, apple. Word dict apple, pen, true. Return true because apple, pen, apple can be segmented as apple, pen, apple. Notes that you are allowed to reuse a dictionary word. Example 3. Um, cats and og, word dictionary. Cats, dog, sand, and cat. Okay, so you cannot separate it because you're missing a D somewhere. So you can do cats, which is here. You can do sand, cat sand. You can do that, but you don't have OG, right? Okay, so fair enough. We just need to find a way to separate the words so that can all the words after the separation can be found in the word dictionary, right? Okay, and you can't do it like backwards. You can only start from the word has to be in the right order. Okay, so I think we can start thinking about this. Uh, let's take an example, okay? This. So this is our example, and our dictionary, of course, is cats, dog, sand, and cat. That's our dictionary, right? Right. Mm, can we break this down into sub problems? Well, that is the thing. Like, you don't know where to cut. But we can decide, I mean, if we cut at any sequence, right? That is something we can do. So that is an action that uh, we can uh, we can we can perform at each word or right after each word. We can choose to cut or not to cut. And these actions, they lead to like a true or false um, subsequently. So let's just say we have this cats and dog, right? Um, we're gonna say we're gonna break it into um, this or this. I'm gonna put a dash there. Okay, the dash means I actually connect them, and this means I have two subproblems. Okay, so this is like separated. mm, these two cases. I'm just trying to make sense of this. Okay, so these two cases they represent two choices. The first choice is to you know put a separator here between C and A. The second choice is to actually make sure that C and A are not separated, right? It all happens right after the first word. Um, yeah, so separated and then not separated. Um, is that a complete uh, uh, categorization of what can happen here? Yes. And then, so with these two, we can move on to, yeah, if this is like, if this is like still true, uh, what do I mean if this is true? If like the word C um, can be can be um, can be found in word dict, right? Whatever is here can be found in the word dict on the left, right? Then we move on to um, further separate, further separate this subproblem uh, into this, right? And this, yeah. So again, this is like another separation here. Uh, we have the first subproblem being okay. We put a separator between A and T, right? So somehow A has to be on its own, and it has to be its own word. Uh, and we're gonna work with the remaining of it. Um, on the other hand, A and T they have to be included in the same word, um, right? And then we move on, separating it. But if it's but if it's not true, we're not gonna move along that route. And if it's this case, we're gonna have to, um, I guess, find a word, right? Find a word. Continue with the CA, and we have to find a word. It's either this or um, or this, right? And so for this case, um, because here we are undetermined, right? We just say, hey, CA has to be combined. Uh, and let's see if CA is a word. If CA is a word, we could move on to, if CA is actually a word, we can move on to, if CA is true, right? If CA is true, then we're going to move on to break the remaining subproblem even smaller. Um, or if or if we have to combine CA and T, then it's another problem. CAT, if we have to combine CAT, um, then it's like, okay, we have to break it down into CAT sandog, or um, CATS. These four had to be sticking together, and so those are our cuts. You know, CATS are now binding. Yeah, so these are the possibilities, right? But in reality, you know what? Let's just now talk about the real dictionary now. In the real dictionary, this is false. This is not true, right? This is false because uh, the word C does not belong to the library, although we wish it to be, but it does not belong to the library. So because of that, um, this line just ends here. And we don't need to go further, right? You know, false because C, the word C does not belong to the dictionary. Does not belong to the dictionary. Um, and then, okay, we're gonna see this branch here. So this branch, so basically this is like a false, right? F, a failure. And the only hope is to work on this branch. And for this branch, we will have to see, okay, another two cases. The first case is to see if, this is true. Like if CA alone can be a word. And this is of course not true again. So because CA does not belong to the dictionary. So this is false. This is again a false case, right? So we just eliminated that case. We just also eliminated that case. So we move on to this case. All right, because we eliminated that, everything downstream of that is also impossible, right? And CAT case. Um, okay, so mm, now we have two ways to do it, and CAT. Lucky for us this time, CAT is true. It is belonging to a our library. Let me just stick with the way we draw things and true. Then we move on. Um, and then for this one, we're going to automatically, break it down into two more categories, two more lines, right? So the first one is going to be uh, uh, um, cats, and then blah 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 afterwards, or this is like kata, right? Kata is like going to be a word, and then blah blah blah. Um, oops, sorry about that. Um, therefore, let's change our, yeah, pen color. Um, and because this is actually true, right? This is true because cat does belong to dictionary. So this is actually valid. So we actually move on to, continue to investigate this change. Um, but we also are not going to give up this branch as well, right? So now we have two branches to work on suddenly. So we could use kind of like I guess, uh, a recursive dynamic programming approach, right? If it's a recursive dynamic programming approach, then we're going to use quite a lot of memory. Can we do a bottom up? Yeah, this is like a top down kind of thing. Can we do a bottom up? Um, I'm thinking. So within these two, between these two, we definitely need to come up with a logic, right? A logic and or logic or I think it's a logic or, right? logic or. So if any of the branch is true, we will say that, hey, it is true. So we're going to return eventually the or condition, right? Or operator of all the possible sub branches. So now let's sit back a little bit. Just look at what we've found. We want to maybe define what is a subproblem. So a subproblem in our case, first of all, the original problem is whether this whole string can be decomposed entirely with words in the dictionary, right? And these two subproblems, well, this ATSANDOG is a complete subproblem, just like the original one, except that it's missing a C in front. So that's a subproblem. But this one here is a little weird because now it's not like a typical subproblem. Um, this is like, this is like an OR condition of an OR operation between this subproblem, right? So I'm just gonna highlight, no, I'm just gonna highlight what I think is a subproblem. So I'm gonna use yellow. So this is a valid subproblem, right? This is a valid subproblem, and this is a valid subproblem. For these ones with a dash in the middle, between two characters, um, they're not our typical subproblem because they are indicating that, hey, um, the two, the first two letters are binding, or like the first three letters are binding, or the first four letters are binding. Uh, let's just, decompose this, right, as a OR operator on one subproblem and and what and an OR condition of um, another two subproblems, of another subproblem and something else. Hmm. So this is a little weird. Let's see if we can express them in a kind of an equation. So let's see, our problem is P, okay? So P of, I guess the original problem is, we can say it's P of 0, right? Because, yeah, we can start with 0 on the left. It is equal to, I guess, an OR operator, right? An OR operator between the true or false between, uh, 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 the first word, right? The first word, which is, uh, P, um, this is like this. Is it like the sentence? How do you call it? We called it the S, yeah, S string, S0, right? S0. So, um, okay, P0 equals to OR of S0. Is it a subproblem? Well, yeah, it's kind of like that. And then P of 1, which means, um, actually, no, this is like, we have a AND operator between an AND operator between um, this and this, and then also that basically just describes the first line here, and the second one is gonna be uh, uh, another or operation between this and this, right? So this is or of and. Wow, this is getting super lengthy. An operation between p, uh, right, as 0 to 1, actually 0 to 2, right? That's the first two characters. Uh, and p2, right? So p starting from, yeah, index 2. Um, 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 and you know, another. So this CAT is combination of two other OR operators. Well, this equation just grows longer and longer, and this is like a recursive relationship, but I think I did not express it well in terms of a recursive relationship of our subproblems. So maybe I'm missing something here. What am I missing? Like, it seems like it could be broken down like this, but but maybe this is not, the most elegant way of breaking it down. Let's try start fresh again, see if we can do something else. Right, so we're talking about subproblems. What if we, whoa, that is quite wrong. Cats and dog, uh, outline, fill. No, we don't need outlines. Okay, so let's make it 0%. Okay, yep, yep. Uh, fill, but no outline. Yeah, let's just redo it. No outline. Okay, yep, just like that. Yep, cats and dog, and see what we can do. Maybe we can separate. Um, right, we can try to see if C is acceptable in the library, and if not, let's see if CA is acceptable in the library, and or we can, if it's still not, we can move on to see if CAT is acceptable in the library. So we're gonna keep growing our word until we find our first acceptable dictionary word, right? This is our first acceptable dictionary word. So we could now put a separator here, say this is our first separation, possibly, right? Because this first word is going to be valid. Um, and then we can use this as a starting point, and then we're going to see if, for example, moving on, if this is a good word, if not, if SA is a good word, or if SAN is a good word, still no. And then we're going to see if SAND is a good word. It turned out it is. So that's the next thing we're going to move to, right? Um, what is the other branch? The other branch, well, we're gonna now give up the CAT and now let's move on to CATS. See if it's a word. And it turned out it is, right? So it will instead go to this branch uh, and and we will move on to find if there's another word down there, and we did find it's cats and, right? So these are the two possible ways to separate these two words, which we just draw, uh, and none of and all of them leads to an illegal word OG down there. So first we started with cat, right? Cat, and then we either choose to take it or we would choose to ditch it, right? Use cat. This branch is called use cat, right? This uh this branch is to not use cat, right? So this is the not use cat. This is the not use cat branch, and the above is the use cat branch, and then cats. Uh, wait, we still have to hold on. I think I'm missing something here. Just to be logically sound, once we found, cats, right? We still have to make a decision of whether to use cats or not, right? So again, we continue with that separation logic, and in branch one, we use cats, and we will find this thing here, cats and org, right? I think this is actually gonna work. So, and this is more elegant. Let me actually just remove. Okay, instead of removing, let's take our logic here and let's move it to a new page. Okay, so this is our new logic. And on our first page, which we're gonna name it properly, we are going to uh, completely clean that. And this is like currently we're giving up on this dot and we're just moving on to um, this next dot that is going to be more promising, I think. Leet 139 part 2. Let's work on it. So cats and dog. This is where we actually we use not use cat, right? So here we found the and keyword, and first is like use and. Wow. Um, mm, okay, use and. Yeah, this is really a little bit challenging for my drawing pad. This is like not use and, right? And for the, come on, for the use and branch, we're gonna do that. And for the not use and branch, we're going to try if we can find something like and org. No, there's no way. So we're at the end of it. So we say this is a dead end. So this is gonna provide a false to us, right? And cats and if we use and as a word, we put a spacer here. And OG, there's no answer, so we're gonna have to produce an F there. And yeah, this here is like no, so we're gonna produce an F. Therefore, uh, if we call um, So we can express now our original problem, right? Return something is going to be, um, this is like our first uh, uh, separation point, right? So our uh, problem zero, let's say our problem zero, which is like, which means um, we place something which means we place something on the left of the zeroth character, right? Yeah, we have to say it. Place a spacer on the left of the kth character. That's the kind of like the subproblem. So on the left of kth character, okay. P0 means place a spacer on the left of the zeroth character. Or the character on index k, right? Yeah. P0 is going to be placing a spacer on the left of the character with index 0. And what we're going to do here is that this is going to be equal to uh, left. So we're going to move on and search for the first keyword, right? Like it'll become at the first separation point, which is the on the left of the character with index 3. So it'll be an or between uh, 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 let's actually just use plus, okay? Because we can use 0 for false and 1 for true, right? And it'll be p 3. Uh, use cat, yeah. So this means like use cat plus uh, 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 then we're gonna move on to the next search, right? What do you mean when we move on to the next search? Like um, put spacer on the left of character with index k. Well, let's not say put a spacer, okay? So subproblem starting on the in the character index with index k. Yeah, so p3, that's what p3 means, right? Um, so the remainder of this is p3 because we start on this, yeah, because 0, 1, 2 is like abandoned. Um, but because cat is accepted, right? Use cat, right? And what is this? This is that we do not separate it there. We're going to find our next separation point, right? Plus p whatever next next index next index yeah, next index. So this next index is actually going to be 4, but how do you find it? Like Yeah, you can pop, you can pop this you can keep popping the list on the left and then see if they form anything, right? Yeah, we can use a list pop, and we can pop the word on the left, and we can keep popping, and once it finds a word that belongs to once it forms a word that belongs to the dictionary, we're gonna say, okay, that's the next index, right? Yeah. Um, right. So, mm, mm, how is this gonna go? Like this separator is like an and, right? Um, yeah, we're gonna have to work with the remainder of the problem. So the remainder is a separate problem, right? P this, P that. Um, I guess in this case we could use dynamic programming to use a bottom-up approach, because now then we could fill everything from bottom up, right? Right. So that is actually going to be better, right? That's actually going to be better if we can use a bottom-up approach. Um, that way we may be able to save some memory. Now, if we do use that next index, we're going to uh, okay. Let's work out, how to find next index. How to find this next index. Um, when mm, when we keep popping keep popping characters from the remaining list, well, or when we keep popping characters, when we keep taking, right? If we keep taking characters from left to right, and it again forms a legal word, then we have found our next index. Then we have found our next index, right? But we could keep searching on and still not finding one, right? Like if we can search the entire length of the list and still not find still not finding anything. So if that's the case, then the not use cat option is going to turn out to be false. But that has cost us a computation of O of n already, because we're looking up already n times in this array. And that's just the one step. That's just step one, right? So so I think this is not a very good heuristic either, because this is gonna be at least um, this is gonna be at least an O of n squared in terms of computation. And I don't like it. I don't like it at all. Can we somehow solve this problem in a more principled way by modeling it with dynamic programming and somehow even with state machine? It worked well in the stock buying and selling case, but um, so what are our states here? Mm, and what are our actions? Our actions, it could be defined um, as whether we as whether we take put a separator down at after one word or not. That is our action. So we only have two actions actually for each step, which is great. But the states, you know, the states are, so there's so many possible states because we have 27 characters and we have, strings, and that's going to be a lot of states if you think about the possible combinations, right? Um, how about let's just imagine this like a game with a character trying to walk from the left to the right, right? And he's holding in his hand like a separator, a divider. So he has to put a separator at the right place so that the word before the separator has to be belonging to the dictionary. Otherwise, the game fails. He has to walk. He has to walk over this entire place, uh, and then eventually all the land that he walked has to be placed, has to be cleared by categorizing them into the dictionary. Hmm, that's also a little bit hard to visualize. Can we just reduce the length of the word because we already have a memory of like the entire word in the entire string in the input. We don't want to just memorize more. We want to memorize less, right? Uh, yeah, we want to memorize less. So we want to be done with the part, and we just throw it away, and we just deal with the rest. The risk of that is that throwing something away may not be optimal, and once you've thrown it away, there's no getting it back. You know, that's the thing. If you throw it away, there's no getting it back. Um, yeah. Th- so in some way, this is similar to actually the stock buying and selling problem, because you need to find like a, a start and an end, um, a start and an end place for each word, and and each of the word has to be valid somehow. In the stock selling up case, each of your transaction has to make you some money, right? Um, and then you're optimizing towards that. And in here, we just care about true or false. So in a way, I guess this is a simpler problem than the stock buying and selling. But then every sale has to be valid. Like you have to find all these uh, characters, make sure that they form a word that is valid, right? So how do you do that? Uh, I think I think previously for the stock problem, we could use like a very um, microscopic view to look at each day's stock value and determine if on that day we could gain something or we could not. But in here, it's kind of hard to determine like a particular word if it's worth adding or if it's worth adding to the existing word on the left, or if it's actually better to just stop and separate it from there on. Um, hmm, it's a pretty hard question, I guess. You know what? I am actually gonna give up because I tried two different intuition and I don't think I'm going anywhere with them. So uh, I'm gonna just go directly to the solution today. See what I can do to learn from them. Of course, we don't want to use brute force, right? Because it's gonna be O2n, that's too bad, and space complexity is too bad as well. Recursion with memorization, is that good? That's whoa, that's still bad. That's still not good. Oh, we're using BFS, breadth first search. Breadth first search is gonna guarantee an optimal, global optimal solution. I learned that uh, from somewhere else, so that's something I know, which is good about BFS. But still, the time complexity is O and 3. It's pretty high. Um, Space complexity is also high because there's the tree. You need to remember that down the tree. Using dynamic programming, is it better? Well, it's not really better, but it is dynamic programming, right? So I'm going to learn from this dynamic programming problem. Okay, now let's take a look. So this intuition behind this approach is that given problem S can be divided into subproblems S1 and S2. If these subproblems individually satisfy the required condition, the complete problem, then S also satisfies this same. Um, for example, if cats and dog can be split into two substrings, cats and the other one is dog, the subproblem cats and can be further divided into cats and which individually are part of the dictionary, making cats and satisfy the condition. Going further backwards, cats and dog also satisfy the required criteria individually leading to the complete string cats and dog also satisfy the criteria. Okay. Now we move on to the process of DP array formation. We make use of a DP array of size n plus 1, where n is the length of the given string. N is the length of the given string. Um, we also use two index pointers. Okay, I and j, where I refers to the length of the substring considered currently starting from the beginning, and j refers to the index partitioning the current substring into smaller substrings, s prime 0j and s prime j plus 1 I. Okay, to fill in the DP array, we initialize the element DP0 as true, since the null string is always present in the dictionary, and the rest of the element of DP as false. We consider substrings of all possible lengths starting from the beginning by making use of index I. For every such substring, we partition the string into two further substrings in all possible ways using the index j. So we have two sets of index. The first index I uh, is the length of the substring s prime, which is the substring from the beginning, and j is the index partitioning the current substring into smaller substrings. Okay, okay, all right. So let me try to make sense of this by trying to visualize it with the new map like that. So let's say if we have Yeah, let's say if we have like well, not like that. Let's say if we have a pretty long word, okay? A pretty long word, and then let's say we place our, this is gonna be our ith element. That's gonna be, right? This is like 0, and this is I, and we gonna have, right, um, index I to refer to the length of the substring starting from the beginning. So yeah, um, this is what, so this substring from 0 to I is our S prime, okay? Uh, and J refers to the index partitioning the current substring into smaller substrings between 0 and J plus 1 to I. Okay, so we're gonna further separate our array into two smaller parts. This is gonna be our J plus 1. So this is our, so these are our two further smaller substrings. Okay, so we're gonna call what? We're gonna call this S prime 0 J. This is what? S prime J plus 1 to I. Okay, right. And to fill the DP array, we initialize the element DP as true, and then since the null string is always present in the dictionary, and the rest of the element of DP as false. Okay, we consider substrings of all possible lengths starting from the beginning by making use of index I. That means we sweep I, right, to make sure we get the first part, the first bulk part, to vary from, the smallest length to the largest possible length. Right, for every such substring, we partition the string into two further substrings, S1 and S1 prime, S2 prime, using J. Okay, so that's what you mean by S1 prime and S2 prime. So, yeah, okay. So we're gonna call this what? S1 prime. I'm gonna call this what? S2 prime. Got it? Uh, and okay. So, in all possible ways, using the index J. Right. Now to fill in the entire DP I, we check if the DPJ contains true. That is, if the substring S1 S1 prime fulfills the required criteria. This is a little confusing. What do you mean if the substring S1 prime contains what? Um, if the substring S1 prime fulfills the required criteria, if the substring S1 prime contains um, contains the fulfills the required criteria. If so, we further check if S2 prime is present in the dictionary. Okay, so we're gonna check the first part of it, see if it fulfills. If both strings fulfill the criteria, we make DPI as true, otherwise as false. Okay, so we first check if this S1 prime is a legal word. Then we check if S2 prime is a legal word. So what? You just did a very small portion of the search. What else do you do? I mean, I'm still confused. Um, there are two nested loops, I know that, I and j, and the substring computation each iteration. So it's, yeah, n triple. Overall, that results in n cube time complexity. Yes. So what do you do with the the DP array here? So you have DP, you initialize it as all false um, with the length of the string plus 1, and you initialize the dp of 0 as true, okay? And then you increase I, and then you increase j, and you see if dpj, which is dpj is going to be the first half of the substring, and dpj and sji, sji is what? sji sji is like s prime j plus 1 I. Is that true? If both of them are like in word set, we're gonna say this dpi is true, and we also break. Break meaning we're going to break this for loop here, the second for loop, and we basically say, okay, we found a true separation for I. As long as we find a possible separation for I, we move on to the next I. Uh, move on to the next I, and basically what we're doing is we are um, we're just moving on and increasing the length by 1, and we try to search if we can find another way to separate that a little bit longer substring. And what is the point? And you keep growing, keep growing. Are you reusing anything? I mean, I don't see you reusing anything. Did you reuse anything? Well, I think, okay, so everything is false. So, um, I think during this, you are somehow updating DPI as true for uh, um, um, DPJ. So how, yeah, this is like looking it up, right? This is like updating the DP table. Um, if DPJ, what does if DPJ mean? DPJ, um, what is DPJ? So DPJ could be true or false. It was initialized as all false, right? And then we're basically growing this DP array, and whenever we find a good separation, right? Whenever we find a good separation, we're gonna mark that I, we're gonna mark that I as true, basically placing a landmark here saying, hey, if we found something that successfully splits these two, we're gonna put a landmark here, say this is true, right? If if we can ever find a successful separation between S1 and S2, we're gonna say, hey, Si is gonna be true, right? Okay. So in the end, we're gonna basically label it. Let's just fill it. If it's true, we're gonna fill it with a color, okay? And then we move on. Uh, so when we look back, for example, when we later grow our, let me just copy this because this is like growing to be a difficult thing to understand. Now, since we've placed our first I as like true or something, right? I I believe, down the line there, we're gonna have a few places where we're gonna have uh, like color stripes, you know, sporadic indices there, here and there. That basically means, well, we can fit two words in there. Uh, and because J starts with what, zero, right? So it definitely includes the case where, this is just one single word in between uh, um, the index, like the first index and uh, the first index uh, and the last. So S J I. Yeah, because S is now like one index short than DP. Like DP is like adding one index to itself. So, right. So now when we are faced with a new problem, like maybe like this, right? So let's say if our new I is here, right? If our new I is here and this is 0, and now we're trying to see if this S prime, if this I here can be colored purple or not. So then we're gonna try to search for a separation between an S1 substring and an S1 prime substring and an S2 prime substring. And see um, if what? If um, if the first part is recorded true in the DP substring and the second part is a one word, right? So if we can find something there, like if we can find a separation that we recorded before, like a one word or whatever word, like um, for example, it um, if we can find dpj, so j, yeah, if we can find this to be, our first s1 prime, right? If this is like valid, and then if whatever is like remaining here is a legal word, right? If this is like actually a legal word, if this is like a s2 prime is legal, right? Is legal. Once this is legal, and the string substring before it was also kind of like a recorded legal substring, right? We're gonna call this DP recorded DP recorded legal substring, and on the right is this legal word, right? This is not any substring. It has to be a word in the dictionary. S2 is a legal word in the dictionary. In the dictionary, then the combined S prime is legal, so we can then color it with the purple color, right? So now we can color it with purple and say, hey, we put a new landmark, we put a new mark here, um, and we can move on, right? And then we move all the way to our last index in this way, and we're just gonna see if like right if our last index in this case it's gonna be like what, m minus one, right? If the last index here can also be found to be a combination uh, of a DP recorded legal substring and a legal keyword right after it. If that is the case, then we have our solution. So yeah, this is like a DP solution. So we're using DP, right? We're using DP as like a substring. I mean like a recorder or a memory to basically record where we have found legal substrings from the beginning to that point, right? Um, DP, this is like recording whether the substring from S0 to SK is a legal, not illegal, is a legal substring, right? A legal substring. Yeah, this is what this this DP this DP of K is going to tell us. Yeah, recording whether the substring from S0 to SK is a legal substring. And we're going to use that DP string to not a string, it's a list of true and false. We're going to see if that is going to, yeah, that is going to help us build a memory of good memories. Um, it's a list of good memories of where things were working, and then we're going to see if our entire string can be broken down into uh, two parts. The first part is a good memory, and then the second part is a legal word, right? Yeah, so that's the okay, that's the intuition. I got it. I mean, it's not easy to come up with because just thinking about how you need to cache a memory like this, like DP, to remember uh places in the string that can be remembered as good memories or good substring ending points, right? Yeah, let me just use that word, valid substring ending points. So this actually makes more sense if we think about it that way, right? These are like or you know valid substring ending points for substring starting at the beginning. Yeah, so this is like more like a valid way of describing it, I think. Yeah, DPK is going to be a valid substring ending points for substring starting at the beginning. And then we keep updating that that list, and then we're going to. So this is like a bottom-up DP. So I'm not gonna lie, this is a bottom-up DP. It definitely is a bottom-up DP. It's just that uh, in this case, we're just keeping it's a weird or like it's a very particular way of remembering things. Of Yeah, it's remembering if oh actually, I mean you know what actually, or you know if the subarray, right? If the subarray from S0 to SK is a valid array, right? So, well, substring, let's see, it's a valid string, right? Right. So this actually makes much more sense now because this is exactly what a subproblem is. Like in, I think in our first attempt, that's how we were trying to formulate it, right? Like we were using this yellow substring as as our substring, and then this yellow substring as our substring. So we were actually trying to go down this way to see if we can solve it, and then yeah, but we didn't do this as a bottom up. This is like a top down approach. So if we actually do this as a bottom up approach, once we prove that this substring is valid, then we can move on and see if the new string can be found as can be seen as a combination of a valid keyword and a valid remaining substring. Yeah, so I guess we almost were there. We were almost there, but we were just missing a few key insights there. Yeah, right. So if we had actually sticked with our substring uh, subproblem intuition, we and worked a little bit harder, we could have thought of it. Uh, but now we only solved it and found it by looking at the solution. So this is a bottom-up DP, right? And yeah, so this is like a bottom-up way of doing it. And now instead of like growing from I guess the first the first keyword, the first character to the last, now I'm actually going to learn from this intuition, but now I'm going to uh, derive it, myself by starting from the end. What do I mean by that? Uh, well, what I mean is that I'm going to use the same representation here, like a string, but and also we're going to do like a bottom-up approach, right? So we're looking at the bottom, the last array, which the last character, which is like m minus one, indexed m minus one, and then well, we're basically checking, okay, if this subproblem is valid, like just having the last element. If it's not, we're gonna label it false there, and then we're gonna look at our n minus two, right, and see if now if this can be a valid substring. So a valid substring or a valid substring, um, yeah. So criteria criteria for a valid substring is the following. So first, um, is that um, it contains a valid word plus a shorter, yeah, a remaining also valid substring. So this is how you reuse calculation, right? And yeah, I think that's it. Like it contains a valid word on the left and a remaining valid substring on the right. So when we're looking at m minus 2, we're asking ourselves, does it have a valid word at the beginning? So we have to search, right? We have to search basically from the first word on, uh, and then to the last word. See if we can find a valid word. And then after we found a valid word, we're gonna see if the second part is like a valid substring, which then we could use the lookup table. So we're gonna use our memory, right? Our memory is a list of length um, um, list of length n, right? Same length as the length of the original string, right? Indicating whether the subarray s mm, 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 yeah, I mean its element let's call it valid after, right? Called valid after. Yeah. So its element valid after k indicate whether the subarray sk all the way to the end, right, is a valid subarray, substring, right? Substring. Whether the substring is a valid substring. Yeah. So this is our memory. Um, a list of lengths n called valid after, and whether the string is a valid um, substring. Yeah. Actually, it's not after. Let's call it valid since, because that is gonna be more intuitive. Yeah, let's call it valid since. Right. We're gonna use a valid since memory to do that, and we're gonna build that valid since all the way and then to the beginning of the array, right? So let's start coding and basically try to re-implement the solution, the DP solution here. Now let's go to Markdown, copy the problem here. Right, so description here, and then we're gonna have our first example, leet code. Yeah, that's pretty good. Let's just take the second one actually. Now the second one is a little bit more representative. Now, let's go to code here. This is our example. And then we will move on to our constraints. Right, there we go. And we're gonna copy our solution template, and then we're gonna have our test case copied here as well. So the function has two inputs, right? And the first problem is like, okay, we're gonna have this, and word dictionary is this, and expect true, right? Right, so we're gonna first try this, and we're gonna try Apple Pen as a second input. Yeah, that's our first test case, and we can start building it. And because we're building it in a bottom-up DP fashion, right? We're just gonna write bottom up DP. There we go. And we're gonna initialize our valid string, valid after. Valid after is going to be, okay, let's first find the length of our string s. And valid after, this is a string of false, right? And it has how many elements? N elements. Okay. And then we're gonna do a for loop. Um, and we're gonna do a for loop on what? On the index of the original array, right? Not the element. You sure about that? Yeah, I'm sure about that. So for k in range, we're gonna start from n minus 1, and we're gonna end at 0. So we're gonna say minus 1, minus 1. Okay, whoops. Yeah, and what we're gonna do in each for loop is that we're going to try to find out. Actually, we're just updating this valid since, and then the way we update valid since is we're gonna perform another loop, right? Just to within each substring. Let me now start some illustration here. So if this is our k, right? This is our k. Um, we're gonna start searching from k to, let's say, m, searching from k to m, and see if from k to m we have a word, right? A valid word. That's the first thing, right? Uh, yeah, first thing is we're gonna see if our from k to m is like a valid word, right? And then, also we want to find if the remainder, if the remain, I'm gonna remove these, right? If the remainder is a valid substring, right? So valid, if it's like a valid since, right? Yeah, because this is where we're gonna reuse the calculation. So this is gonna be valid since what, m plus one, right? This is where we're gonna reuse that. And then if if both these questions are are true, um, so yeah, if true, we're gonna say our valid since of k is also true. Else, uh, else, I mean, it's already false to begin with. Else do nothing, right? Else just to move on. We also, since we're also searching like the m index, we also want to break, right? Break the m loop. You know, that's if true. We break the m loop. Else, um, right? This is like we're on the k loop, and if we're true, we don't need to look further. We just assign this equal to true, and then we break the m loop. Else we else we just move on, right? Move on with next next m, right? Next we move on with the next m. Yeah. So this is basically our loop. Um, so we're gonna do for m in range starting from which um, um, from k plus 1, right? Because the first thing somehow has to be a word. I mean, the the case character is something new. You have to put it somewhere. What if like itself? What if like the k word itself is like a single character word, right? It's possible. So we don't want to miss that. So M indeed it can start from just K itself, right? Yes, yes, yes. So we're gonna start that from K itself all the way um, up to n minus 1, the last word, right? We're going to search everything, n minus 1, because it's possible that from k to n minus 1 is like a whole word, and then the valid since is just empty, right? Yeah, valid since is going to be empty. Now, valid since n plus 1, well, we need a valid since, I think we need to kind of like append valid since with one more index, with one more with one more with one more element, right? So this is gonna be n. So why is that? Because we want our kind of like the valid since. We want our valid since n, valid since no, valid since n to be true, because you know there's no words afterwards. I mean, that has to be true. Like you can separate you can put separators after the end of the original list, whatever you like, however you like. So yeah, so that's a modification. So we're gonna say modification, modification. It's a slight modification. What we're gonna do, we're gonna append a an element of true at the end of uh, valid since. This will make this will basically cover the case that the entire substring from k to m is a word, is a valid word, and valid since is just an empty, it's just an empty string. No, not is, represents just an empty string, which is of course valid or true, right? Yeah, so that's what we're gonna do. We're gonna make our valid since having one additional element in there. So valid after false, and let's do n plus 1, right? And valid after minus 1 is true. Yeah, this is like a special treatment here. The last element, assign the last element to be true. Yeah, representing something. Yeah. Now we're ready to perform something. So now m can go from k all the way to n minus 1, which is the last element here. Right. And then we're going to say here, if, right, if from k to the m, right, if um, s from k all the way to m, right, is in, word dict, it's in word dict, and the second part, which is the remaining part, from m plus 1 on is valid, right? M plus 1 is valid. If that's the case, then we assign valid since of k to be true. We also, right, we're going to update. This is like update valid since at k. And also we're going to break the m, yeah, break the m loop. Right. What else do we do? Else we just move on, so we don't need to do anything. Right. So that's it, right? That's pretty much it. And in the end, we're just returning what? We're returning valid since of 0 because we want to know if it's valid since 0. Right. Yeah. That's about it. Let's see if it's true. There's something wrong. Valid since is not defined. Valid since. Oh, valid after. Okay, I should say valid since because that's more accurate. Okay. Valid since. We're expecting true and we produced false. Okay. So there's something definitely not right there. Let's start with our breakpoint and just break through it. See what's going on. We're gonna put our nice breakpoint here, right after the two for loops, right? And I don't know why it's reacting so slowly. All right, so we're gonna put a breakpoint there, and we're gonna step through it. All right, now here we go. Here we go, and so we'll be looking at what? We'll be looking at what is the valid since. It should be like a list with all false and the length of what? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. So yeah, the valid since array is a one element longer than the original array, so it's 14. And the last one is true, which is true. Yeah, and then we're at k equal to 1 right now. This is like, yeah, k equal to 11. Okay, yeah, k equal to 11. So why is k equal to 11? Yes, because it's the last element. It's e there. So m is in the range from 11 to 11. So m is equal to 11 right now. So if k equal to that is in word dict, definitely it is not. So we're gonna just skip this, right? So we're not updating anything. And now, wait, why is, oh, sorry about that. I think I found the problem. Um, so we need to say range. Yeah, it should be that. Like yeah, it should be n because the last element we want to visit is n minus 1, so it should be an n here. Now, this might make sense right now. Yeah, it's producing true now. So let's put um another test case into it. Let's put leet code in there, right? Apple and apple, cats. Let's put the cats and dog example in there. Yeah, this is like the next example. And what is the library? The library is pretty large. Okay. Um, this is our second one. So this is the string, and this is the library. I don't expect it to produce false because you couldn't find the right one. Yep, that's correct. And let's put one more, the leet code. Right, let's put leet code as the first example here. Leet code, and in our library we're gonna have a leet and a code. Expect true. All right. So let's try that. True. Okay. So I think this might be working, but let's just put some documentation here. Version 1 taken from solution and a bottom up DP and its time complexity. Unfortunately, in this case, it's going to be O. You see we have two for loops, and in each for loop, uh, we are doing an if condition uh, and then we're checking valid since. So it's going to be O(n) squared maybe. And then space complexity. This is definitely O of n because we're keeping an array valid since that is n plus 1 distance long. Right, so we're just copying this solution into Python solution, run the code, accept it once, accept it again, let's submit. Accepted. Yeah, word break. So let's just run it once more to see its performance. Once more, performance. Okay, so it's an average code. All right, so that's it, guys. So we, as a summary, we today looked at this word break problem, which is a little bit difficult for me because I did two attempts. I did the first attempt trying to, trying to work it uh, in a cascading down or a top down kind of DP solution approach. But I overcomplicated stuff, I guess, by looking at how the first few elements can combine, as well as how the remaining substring is valid or not. So uh, I guess my thoughts weren't as crisp enough in this, so I actually gave it up and I moved on to a second set of intuition, which was like trying to place spacers in between these words and try to then break them into categories. But then I realized that this is at least O(n) squared, right? Even if we can finish this. So I again gave this up, and then I looked at the solution, which is to my surprise, even the DP solution also has a complexity of O(n)(3). Oh, okay. Substring computation. Okay, so it's O(n)(3). All right. You said because there's two for loops and then there is a substring computation at each iteration. Okay, so you consider this actually being a n-step computation. All right. Okay. All right. So yeah, to my surprise, even the best dynamic programming solution that we've found here has a pretty high time complexity, as well as a not cheap space complexity. But anyway, we re-implemented, try to re-implemented that code, but now in a different direction. So uh, what I mean is that the solution went from the left to the right, whereas I went from right to the left. And yeah, the intuition worked, and we're here with an average performance submission, and that's it, days. So I guess the takeaway is that You just need to find a good intuition, and yeah, if it doesn't seem like it's going anywhere, you definitely should try something else. But if if two or more like intuitions are not working, maybe you should just go back to the belief that a dynamic programming solution exists and try to, dig a little deeper with your dynamic programming thinking to try to find a sub problem that can be solved and how you can reuse that sub problem to solve a more complicated, larger problem and go from there. Okay, so that's my 2 cents, and I'll see you in our next video. Peace.